All right, good morning. Today we are covering lesson 7.06, Can Vectors Change Size? And what's great about this lesson is we're not actually learning anything new. We are just combining some of the skills that we've already learned throughout Module 7. And then we'll continue putting these skills together on Thursday during our 7.07 live lesson when we go into all the applications of vectors. So by the end of this lesson today, you will be able to calculate the magnitude and direction of a vector scalar multiple and the sum of two or more vectors. So if you notice, all we're doing here is calculating magnitude and direction. We learned that in 7.01, and we've been using it since then. So like I said, today should be a pretty great lesson. So we're going to start with a review warm-up. Then we'll go into vector scalar multiples. Then we'll look at the sum of two vectors, and then we'll go over an example of if there's a sum for three vectors. All right, so for our warm-up today, some of you have already completed it because you got here early. If you're not in the Desmos yet, no problem. I just put the link in the chat box. All you're doing for this warm-up is you're calculating the magnitude and direction of vector AB. And vector AB is given to you in component form as -3, 5. Here's the typed up solution if you'd like to see it. And J, here's where I drew my vector and then labeled the components individually. So you can see that if you're using the magnitude formula, it's the same thing as Pythagorean theorem. And again, I've got the direction formula. And in case you don't have it saved, I just put the link to the formula sheet in the chat box for you. Great. So I would say 98% of students got both of those correct, which is phenomenal because our objective today is just to calculate magnitude and direction, which you already know how to do. And just a reminder that this table is on the formula sheet for you if you aren't sure how many degrees you need to add, if it's 180 or 360, just depends on the quadrant. And you can always reference this if you'd like. You can also just think about it logically to check your answer. All right, so the first thing we're going to do in this new lesson is look at scalar multiples, because that was our first objective, is to calculate the magnitude and direction of scalar multiples. So in Desmos, you have vector v, which is given to you. It's just this horizontal vector that has 4 units in the horizontal direction. So if this is vector v, I want you to draw an example of what vector 2v would look like. And so this goes back to our lesson 7.03 when we looked at what happens when you multiply a vector by a scalar. See if you all remember. If I multiply vector v by 2, what's going to happen? Nice job, Jay and Grace, Bryce, Lauren and Maya. Your vectors are looking great. Now don't change vector v. This will stay the same. I want you to add, if you use this little construct button, you can add a new vector. So that way we can compare them pretty easily. All right, good. Now I want you to construct a third vector, and I want this one to show vector -2v. So all we're doing now is we're just changing the sign from positive to negative. Great. I'm going to pull up this example that a student has drawn. So vector v was our given. If we wanted to have vector 2v, we know that all we're doing is we're multiplying the magnitude by 2. We're doubling it. So if this is vector v, then the example they drew right above it would be 2v. Notice that the arrowhead is still pointing directly to the right. The direction hasn't changed. All we've done is we've multiplied the length by 2. And then for the third example, where they drew vector negative 2v, we can see that the magnitude, the length of it, is twice the length of the v. But notice the arrowhead is now pointing to the opposite direction. Because when we change, remember when we change the vector from positive to negative, it flips the direction in the opposite way. It changes it by 180 degrees. So thanks for drawing those different examples. Again, this isn't anything new. This is just reviewing what we covered in 7.03. But we're going to combine this knowledge with our knowledge of finding magnitude and direction. So based off of this, what do you think? I mean, based off of this, you can see visually that when we multiply a scalar to the vector, all that changes is the magnitude. Unless we're multiplying by a negative, that's going to change the direction, and it's only going to change the direction by 180 degrees. There's never going to be an in-between. It's going to be completely the opposite direction. So I really liked this example from your online lesson. So this is just copied and pasted from your online lesson, where same thing, they give us a vector v, a vector 2v, and a vector negative 2v. And the only difference is these ones are at a diagonal rather than straight horizontal. But you'll see if vector v is this 4, 3, then we can find the magnitude of that using our magnitude equation. So we can see that the magnitude of v is just 5. And then if we compare that to 2v and negative 2v, as you might predict, it's just going to be twice. So 2v has a magnitude of 10, negative 2v has a magnitude of 10. And remember, magnitude is always, always positive. So it doesn't matter that we're multiplying this second vector by a negative scalar. Magnitude is always positive, because again, magnitude is just the length of that line. And so you'll see this formula sometimes throughout your online lesson, where k is just a scalar. And this is just saying if you have a scalar being multiplied by a vector, then the magnitude is just the magnitude of that vector multiplied by the scalar. And notice everything's in absolute values because magnitude is always positive. All right, so we have vector u is equal to 10, 12. And we want to calculate what is the magnitude of negative 2u. Do I have any volunteers who want to take the mic and walk us through what they would do to solve this? I saw Jay raised his hand. Any other volunteers? Awesome. Maya, go ahead.
So first thing you can do is find the magnitude of u. So that'd be 10 squared plus 12 squared, all under a radical. And that'd be 100 plus 144 under a radical, and that would get you square root of 244. And then you can multiply that by 2 or negative 2. which that comes out to 31.24.
Perfect. And that's as easy as this is. We have a vector. We calculate the magnitude just like we did in lesson 7.01. And at this point, you can keep this as a radical just to save any rounding error for the end. I liked that Maya did that. And then we take that magnitude and we just multiply it by the absolute value of our scalar. So -2 is just 2 when you take the absolute value of it. And then in our very last step, we do want to get a decimal answer. Typically for magnitude, they're going to have us go to the thousandths decimal place. So great explanation step by step. And here I've typed up just so you can see the two different approaches. So this was the approach. Method 1 is the approach that Maya explained, where we first just calculate the magnitude of u. And then our last step is to multiply it by the -2. And you'll see that method 1 is the approach that I'm going to take throughout the whole lesson. And you'll see why it can actually save us some time when we calculate direction. Method 2 is if we take our original vector and we first multiply it by that scalar. So remember, when you multiply a vector by a scalar, you're just multiplying each component. And I noticed I dropped the -2 somewhere, or the negative, so this should be a negative in there. And then after we get that in component form, then we can just take the magnitude of that. And again, these should be negatives. Thankfully, it doesn't change my answer because they're squared. But you'll see both approaches give us the same answer. And that makes sense because conceptually, we're doing the exact same thing. All right, so going back to those original vectors, vector v, 2v, and -v, we already compared magnitude. The magnitude is just multiplying the length of the line. And when you're looking at magnitude, the sign doesn't matter because we're always taking in the absolute values. But now let's look at direction. So when we compare the direction of these vectors, what do you notice about the direction of 2v versus v? Exactly, they're the same. They're exactly the same. They're pointing, in this case, directly to the right at 0 degrees. What about direction of -2v compared to our original vector v? Right, they're the complete opposite direction. We've gone from 0 degrees. Now this is pointing at 180 degrees. So conceptually, we already understood this, but when you have a negative, it is just going to flip your direction into the exact opposite direction. And so if your vector is pointing in quadrant 1 or quadrant 2, if your scalar is positive, then that's not going to change the direction at all. The only time you have to worry about the direction changing is if your scalar has a negative. And if that's the case, then if it's in quadrant 1 or 2, we're going to add 180 degrees to get that theta. And if it's in quadrant 3 or 4, we're going to subtract 180 degrees to get that theta. All right, so here we have vector W, which is 15i plus 52j. And so we can't forget all the different forms of writing vectors, because you might see problems that have component form, linear form, or trig form. The process is always the same though. So here they want to know if that's vector W, then what is the direction of 3W? So do I need to first calculate vector 3W? Is that where we should start here? Couple of no's. Why not? What's your reasoning for no? You're on the right track, Jay, but we don't actually have to multiply it by 3. True, Grace. What's it have to do with direction? Grace, can you take the mic and share what you mean there?
Yeah, because the question is like asking for the direction. It's not asking for the magnitude.
Right. And if the direction for this vector, if we're multiplying a scalar of +3, what do we know about the direction of W and 3W?
It's going to be the same.
Exactly. It's exactly the same. So we actually can work smarter here and not harder. We don't even need to calculate vector 3W. If we're solving for the angle and we know that the angle between them is the same, we can simply find the angle of vector W. So inverse tangent of our y component divided by our x component. And that gives me 73.909. But I've got to check what quadrant, which quadrant does this fall in? Well, because my x component and my y component are positive, this is quadrant 1. So I don't need to add anything. This is my direction for vector W, which means this is also my direction for 3W. Because we know that the magnitude is changing, however, the direction is exactly the same. And so I've put on my answer slide a visual here to help you think about this. And when I solve these, I actually do sketch the vectors just to make sure I'm correct. So if I sketch W, and I know that the x is positive and the y is positive, I know that's in quadrant 1. And it's not to scale, this is just a sketch. So I sketch W, and then I think, okay, so 3W is going to be in the exact same direction, it's just going to be 3 times as long. And if you do that first, that sketch, it can help you work more efficiently. And of course, check your answers. So here I saw they were in the exact same direction. I just calculated using vector W. Because it's in quadrant 1, I didn't have to add anything. And again, because it's a positive scalar, going back to this table, because it's positive, it's the same direction, if you want to use the table to help. All right, so going back to Desmos, here I've completed a problem with finding the magnitude and direction. However, there's an error in both of my steps. So I just want you to walk through step by step solving the magnitude and direction. If you're given vector t is -16,9, and they want to know the magnitude and direction of -4t. So walk through step by step, and when you spot the errors, just circle them on the Desmos, and you should be able to also write if you want to make corrections. And I see we've dropped some students from that activity, so I'm putting the link for the Desmos back in the chat box. Remember, this is your time to practice and make mistakes and learn from those mistakes so that when you get to the assessment later on the homework, you'll be good to go to get 100%. So if you're interested in proving that you are smarter than your teacher, raise your hand, I'll take volunteers. We'll start first with magnitude and what the error is there. All right, Zachary, What did you find?
Magnitude shall never be negative. So when you do multiply negative 4t times the magnitude, -4 shall be turned to +4, so she'll just be positive 73.430.
Good. Very nice job. And I think it's really easy to forget those absolute value symbols when we're, chugging away at our math. So just make sure magnitude is always a positive answer. And so looking at from the beginning, I calculated the magnitude. I've got the x component squared, the y component squared, took the square root. So that part is all correct. But like Zachary said, just made that mistake here, forgetting to take the absolute value of -4. So this should be positive 73.43. Great job. All right, what about direction? I know direction is always a little bit trickier. Jay, go ahead.
So I had my hand raised because I thought I was super big brain earlier. I was like, wait a minute, it should still be the same direction. Looking at it now, I realized, hey, it's a negative, meaning it should be the opposite direction.
So you're still big brain. You're just catching your own mistakes.
Yeah.
So look step by step. Is this first step correct?
Yes.
Okay, that is correct. We took the inverse tangent of the y component divided by the x component. That's correct. If we're finding the direction of t, the original vector, I need to do something to this to get the direction of t.
Add 360.
Check which quadrant it's in. So negative x, positive y.
That'd be quadrant 2.
Quadrant 2, which means we have to add what to our direction?
180.
Good. So we add 180 to this. The true direction of vector t, our original direction, is 150.642 degrees. So if we now want to find the direction of -4t, what you had noticed was because it's negative, they're in the exact opposite direction. So what do I have to do from my original direction to get the direction of the new vector, -4t?
Would you subtract 180?
Well, if it's in quadrant 2 and it's negative, we're actually going to add 180.
Okay.
And you can use the table, or like I said, what I like to do is if I sketch this is my vector t, then I know my vector -4t is going to be 4 times the size, and it's going to be in exactly the opposite direction. So I can see that this is going to be in quadrant 4 when I'm done. So if I have 150 degrees, I know I need to add 180 to get me there to that 4th quadrant. And so this would be the direction of -4t. So nice job, Jay. You're still big brain, like all of the other students here. That's why you're here in pre-calculus honors, because you have the capacity and more than the capacity to do all of this complex math. So let me switch to the correct answer slide. So you can see here, I've sketched my t, and then I sketched my -4t just to give me an idea. So I can see that the magnitude is going to be 4 times as large as the original. And then for the direction, it's going to be in exactly the opposite direction. So I found the direction of t. But remember, anytime we're doing direction, we have to think about the quadrant. So because that was in quadrant 2, I had to add 180. So here's the direction of vector t, the original. And now if I want the complete opposite, I need to add 180 to that to get the direction of negative 4t. All right, so moving on to the next section, we're looking at adding vectors, which again, this isn't new. We did this in 7.03, which was all about adding and subtracting vectors. So today it's just going to be a little bit different, but the process is still the same. So just to refresh your memory from that last lesson, when we are adding vectors, we just add their like components. So we look at vector u and we look at vector v, and we'll combine their x components and we'll combine their y components. And this formula is on the formula sheet for adding vectors. And so the easiest way to do this is write them both in component form, where v is 2, 8, and u is 6, -4. And then we know we just add the like terms. So 6 plus 2 will give us 8, and then -4 plus 8 will give us 4. So that was simple enough. Now, remember, our objective today is we're just calculating the magnitude and direction. So once we have that sum, that vector sum, we know to calculate the magnitude, we would just use our magnitude formula or the Pythagorean theorem. So we take our x squared plus our y squared, take the square root of it. That will give us our magnitude. And if we want the direction, we just use that inverse tangent formula, where we take our y component divided by our x component. When we get that answer, we've got to check first which quadrant is our vector in. So our vector sum here, 8, 4, that would be pointing in quadrant 1. And because it's in quadrant 1, we don't actually have to add anything. This would be our vector direction. So does everyone remember that from a whole week ago? This is all we're doing for the rest of the lesson. And then just to remember, we did look at it graphically. When you're adding vectors graphically, we have our u vector plus our v vector, and that addition, that resultant, goes from the initial point of the first vector to the terminal point of the second vector. And so we can see if our direction is indeed pointing in quadrant 1, and we can think of it visually as well. So the only difference today is that instead of giving us the component form or the linear form of the vector, we're going to have the trig form in a way. So here's our first practice. We have vectors v and u as shown in the table. And so for the vector, we have the magnitude and we have the direction of each of them individually. But our question is asking us to find the magnitude and direction of their sum. Now, unfortunately, we can't just add down the column because vectors don't work like that, right? We've got to look at their individual components. We can only add the x's, we can only add the y's. So what do you think our first step will be to be able to add these two vectors? So some people said putting them in trig form, combining like terms. So in order to combine like terms, we first have to put them in a different form. And you can choose, you can put it in trig form, component form, linear form. The important thing is your first step is you need to find the components of each, because we can only add the like terms. So we can only add the horizontals and we can only add the verticals, which means we need to know the horizontals first and the verticals first. And then we can complete steps 2 through 4 like we've done before. We can add them, and then we can use the magnitude formula to calculate the magnitude, and we can use the direction formula to calculate the direction. So for step one, and no, Matthew, you can't just add, like I was saying, you have to, when you're adding vectors, remember, you can only add the like components. So unfortunately, we can't just say, oh, our magnitude, we add these, our direction, we add these. That's not going to give you the correct answer. We've got to break it down into components. So to do that, my first step is to rewrite these vectors with their component form. And I prefer using component form just because I think it's easiest and it's easy to keep organized. But you're welcome to write it in linear form, trig form. All of those options are fine. So for my horizontal, if I have this vector, I'll sketch it down here. Vector has a magnitude. Vector of magnitude u is 25, and its angle is at 40 degrees. If I want the horizontal and I want the vertical of it, I've got to go back to perfect right triangles, like trig when we did the last couple modules. If I want this horizontal, I know that the horizontal piece is going to be 25 cosine of 40, because cosine is your adjacent over your hypotenuse. The vertical over here, which is across from my angle, is going to be, and I ran out of room, it's going to be 25 sine of 40, because sine is opposite over hypotenuse. And the great thing is your horizontal is always going to be cosine, your vertical is always going to be sine for our work. So for vector u, if I'm rewriting it in component form, I would have 25 cosine of 40 degrees, and then 25 sine of 40 degrees. And then vector v, same thing. I have my magnitude times the cosine of my angle for the x component, and then the y is the magnitude times the sine of my angle. And I actually just leave them in this form. I don't calculate that and put a decimal because I don't want to have that rounding error. So that was step one. I've written them in their component forms. Step two is I add them. I find the sum of u plus v. And remember, we only add the like terms. So if I'm adding my horizontal components, I'm going to put in my calculator 25 cosine of 40 plus 18 cosine of 130. And all of these are degrees, so my calculator's in degree mode. And when I do that, I do get a decimal of 7.581. And then to add my y components, I take 25 sine of 40 plus 18 sine of 130. And again, that will give me a decimal of 29.858. So that's step two. I've summed the vectors. And then step 3 and 4 is, now that I have that vector sum, I'm only looking at the sum vector. Now I can calculate the magnitude and the direction. So for magnitude of u plus v, square root of my x squared plus my y term squared I get 30.806 for my magnitude. And then for direction, We're just calculating the theta of that sum. So it's my combined y minus or divided by my combined x. So when I get this answer, I get 75.754. But again, anytime you're calculating direction, we've got to think, what quadrant is this in? So because my x is positive and my y is positive, this is in quadrant 1, which means I don't need to add anything to this. And that is my direction. So all of the steps 2, 3, and 4 are what we've done before. The only new part here is step 1, where we're given the magnitude and the direction, and we just need to write the horizontal and vertical components for each of those vectors. So I do have it all typed up for you and color coded. So you can take a screenshot. And step 2, for the question in the chat box, all I did was I added the x components. So that's why I put these both in blue. So you could see that when I add those together, my result is 7.581. Then I add the y components. I kept those in purple. And the result, when I add those two, is 29.858. Because remember, when you add vectors, you can only add their components. All right, so if you hop over to Desmos, we've got another practice like this that you're going to try, but all you have to do is order the steps. Find the components, add them vectors, then you can calculate the magnitude, and then you can calculate the direction. So for this solution, I did write the given vectors in a table just to make it clear. You're welcome to do that, but it's not required. If you just look at your statement, you can probably write your vectors that way. But I like the table, it just makes it nice and clear. So for step 1, find the components. So I take my magnitude times the cosine of the angle for the x, and then my magnitude times the sine of the angle for my y. I do the same thing for my second vector, magnitude cosine of angle, comma, magnitude sine of angle. Step 2 is I add them together. So when I add vectors, I can only add their horizontal components. So when I add these two, I got negative 25.625. When I add the verticals, I got negative 7.322. Step 3 is calculate the magnitude. So now that I have that resultant, I can use my magnitude formula, plugging in my x squared plus my y squared, taking the square root of their sum. Should always be a positive answer. And then last step, calculating the direction. So using the inverse tan of my y divided by my x of the resultant gives me 15.948. But like we said, that is a negative x, negative y. We know this is in quadrant 3, which means we need to add 180 degrees to get our true direction of that vector. This is our last example, but we're going to go through it step by step. So here, they've given us vectors P, Q, and R. So this time we have 3 vectors that we need to add together because they want to know what is the magnitude and direction of P plus Q plus R. So the good news is the process is exactly the same. It doesn't matter if we're adding 2 vectors, 3 vectors, or 100 vectors, which if you were using vectors in applications in physics or engineering, you could have 100 or more vectors that are being combined. So thankfully for us, we're only going to do examples with 2 vectors or 3 vectors. So go ahead in Desmos and complete step 1. Step 1 is we need to find the components of each vector. And when you type in your answer and hit submit, it will pop up the correct answer so you can check your work as you go along. But things are looking really good in the Desmos. Alana, Victoria, Ansley, great answers. Caitlin, Allison, Roman. Great, 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 great. We've already got a lot of students already answering the last vector. Give you about 30 seconds to write all 3, and then we'll go over the answers. Exactly, Nathan. It's the exact same process. Now we just have an additional vector. All right, can I get 3 volunteers to annotate on the screen? What is vector P, vector Q, and vector R in component form? Where are my volunteers? Haley, if you could do P. Maya, if you could do Q, and John, if you could do R. So they've given us the magnitude and direction of each of the vectors, which means we're going to have to use some trig to figure out what are the horizontal and what are the vertical components of each. Perfect. We've got vector P in there. Hopefully Q and R are coming. Perfect. We've got vector Q. And John, I see you wrote it. Are you able to move your answer over so we can see it? Oh, you can't move it over. That's all right. You've got the first number correct. So here are our vectors. P and Q, we already had on the screen. R, just to help John out because he wasn't able to move his answer. 6 cosine of our angle 325. And then of course the Y is 6 sine of our angle 325. All right, so moving on to step 2. Now you need to add these vectors. So what is the sum of P plus Q plus R in component form? And for your decimal answers, you go to the thousandths place, please. And again, I like to keep my components in the trig form so that when I add, I can just add this all at once without having to worry about any rounding error. 10 cosine of 145 plus 12 cosine 90 plus 6 cosine 325. And then same thing for the horizontal or for the verticals. Keep it in trig form so you can add all of them up in one step. Good, and just don't forget, if you're writing it in component form, put those angled brackets so we know that we're still talking about a vector. And then I'll take a volunteer who wants to write in the correct answer on screen for us. Go ahead, Grace, you've got the right answer with the correct rounding as well. And don't forget, if this is component notation, Grace, what should you add to your answer? Same way you wrote it in the Desmos. There you go. Angled brackets. Perfect. So when we add those three vectors up, we're adding just the x components together. We get negative 3.277, just like Grace shared. And then when we add all the y components together, we get 14.294. So now we're on step 3, which is calculating the magnitude. So once you get to step 3, you can ignore all of those individual components, all those individual vectors, because now we're only dealing with the resultant. We're only looking at the sum. So now that we have p plus q plus r, we want to calculate the magnitude of that. So you can do your work either in your calculator or on a piece of paper. Only put your answer here into the box. Wow, you guys are getting fast at this. That's great. Now that we've calculated magnitude and direction many, many times. Do I have a volunteer who wants to type their answer on screen? Go ahead, Chris. And thank you, Matthew, for sharing that. If you're having troubles with the web calculator, Matthew just put in the chat box what he's typed in to get the correct answer. So maybe check the parentheses, make sure your parentheses look similar to what he used. All right, thank you, Chris. When we take negative 3.277 squared plus 14.294 squared, we add them together, take the square root, we do indeed get 14.665 rounded to the thousandth place for our magnitude. And then our last step now, your very last question on the Desmos, calculate the direction. So again, we can ignore all the steps we've done for step 1 and step 3. We're only looking at the resultant vector. We want to know what is its direction. You'll use your inverse tan formula, but just be careful. You've got to think about what quadrant is this resultant vector pointing in so that you can get the correct direction. So I need one last volunteer, not only to write your answer in, but explain to us how you got your answer. All right, Jay, finish this off today.
Hi. So what I did was I did 14.294. Hold up, I can write this. So 14.294 and divided that by 3.277. And I got a funky number, but I already erased my calculator. It gave me a number, and then did the inverse of tan. Sorry, trying to go back on what I was doing. Which gave me negative 77.088. Yeah, because that's a 6 next to it. And then you add 180 because x is negative, but y is positive.
Good. And when you add 180, what do you get for your angle?
You get 102.91. When I did it, I got 912. But also I didn't round this number. I just left it how it was in the calculator and then added 180 to it. So I believe it being different in Desmos is because this number was rounded.
And that's exactly correct. And the only thing I'm going to add here, you said taking the inverse tan, but I'm just going to write that in front. So we know that not only did you divide these numbers, you took the inverse tangent of their motion.
I was about to write it and I was like, I don't know how to write this, so it looks nice. And then I just moved on.
Yeah, we're fine. And I have it all typed up too. So all of the steps combined. Step 1, finding the components. Step 2, adding them. Step 3, finding the magnitude. Step 4, finding the direction. And so the only, like I said, the only new part is step 1, where we're finding the components. Once we add them and we get that resultant vector, this is just going back to 7.01, where you find the magnitude and you find the direction. And so for magnitude, typically students do really well with that. The direction is always a little bit tricky because once you get that answer from the inverse tan, you have to think about the quadrant that it's in and make sure if you need to, you add the 180 or the 360. And just be careful because, you know, if you're rounding at this step, that's going to affect your answers throughout. If you're rounding each of these, that's going to affect your answers throughout. And that's why I don't put these as decimals. I keep them in trig form and add them like that just to try and minimize the rounding error as much as possible.